Okay, example 49. The gantry structure, this is the gantry structure, is used to test the response of an airplane during a crash. Okay? As shown in the figure, the plane having a mass of 8 megagrams, which is 8,000 kilograms, is hoisted back until theta equals 60 degrees. So basically this airplane is pulled back, it is attached to this incredibly strong cable, and it is fixed using this cable AC. Alright? Then at some point this cable AC is released, it's broken through or just released, and this airplane then swings down until it crashes into the ground. And then the engineers obviously monitor a bunch of things. Determine the speed of the plane just before it crashes into the ground. Okay, at theta equals 15. So the angle over here is 15. Also, what is the maximum tension? So first question is VB. What is the velocity of the plane just before it hits the ground? And second question is, what is the tension in this cable at B, right? What is the maximum tension developed in the supporting cable during the motion? All right. So neglect the size of the airplane and the effect. Okay, so again, the first question I ask are, what are the forces acting? What are the forces acting on this plane? Well, here's a free body diagram. We can see that there's weight and the tension in the cable as this plane moves from A to B in this curvilinear motion. We've got the weight and we've got tension. So weight, we know weight is a conservative force. And tension, I haven't covered tension yet, but tension in this case, because it is always perpendicular to the direction of motion, right? Tension is always perpendicular. Tension is called a non-working force in this case. Non-working force. It does no work. Remember, in this case, anytime a force is perpendicular to the direction, if there's your force and there's your delta S or your velocity, that force that's perpendicular does no work. Okay? So we're not saying tension is a non-working force. We're saying in this case, because tension is perpendicular to the direction of motion, it is a non-working force. I warned you. Okay, because some of you will just remember tension is a non-working force, and then in other problems, you know, where you've got something and you've got tension and it's moving this thing up, then you say, oh, but tension is a non-working force. No. Only if that force is perpendicular is it non-working. Okay, I think you got the idea. So because this is non-working, and because we have a conservative force, we can use the conservation of mechanical energy. And that's what we have here. Okay? The total mechanical energy at A should equal the total mechanical energy at B. Alright, so what is the initial kinetic energy? 0. And in this VA, remember V is potentially equal to VG. I like the word potential because it's a potential function. So it's equal to Vg plus Ve. This is the potential energy due to gravity, potential energy due to a spring. But do we have potential energy due to gravity? Yes. There's weight here. What about due to spring? No, there's no spring force acting in this system. So we're only going to have potential energy due to gravity in this problem at state 1 and state 2. Now, what do you do when you're trying to calculate potential energy due to gravity? Remember, it's weight times W, and we want to identify our datum. They identified the datum there. So here's our mass piece. It is below the datum, so we're going to have a negative potential energy. And what is this? So we're going to have minus W, the weight, times this height over here, which is 20 cos 60. Okay? So there's my weight, mg times 20 cos 60, and it's negative because it's below the datum. And there's no spring force, so there's no potential energy due to the spring. So this is all at state B. What's happening at state A? What's happening at state B? Just before it crashes, we again, now we have a velocity component, or the kinetic energy at state B, half mvb squared. And then this particle is moved even lower relative to the datum. So we're still going to have negative potential energy because it's below the datum, minus mg, minus w, 20 cos 15, because now the height is there. Okay? It's that component there, 20 cos 15. And the only unknown we have is VB, and VB is equal to 13.5. Okay? Now, the second question is, what is the tension? Well, the tension should be the maximum at B, because if we look at the equations of motion using normal and tangential components, then here's our free body diagram. There's our normal direction. Sum of the forces in the normal is mass times acceleration in the normal. So we got T, that's your tension in the positive direction, minus W cos 15. Okay, those are the forces. Is mass is mv squared over rho. Okay, if this rho is constant, then the higher your velocity, the higher tension is going to be. Sorry about that. I don't know why that came up. You turn that off. Okay, and we calculate our tension at B, equal to 149 kilonewton. Okay. So one exercise you could do, guys, is you could change your datum. Put your datum there, and you're meant to get exactly the same answer. So the question is, why does it not matter where we put our datum? It's because we're always looking at changes from A to B. So if you measure it from there, or your datum from there, you're going to look at the same change, okay, from A to B. So try a different datum, and you need to get the same results.